Okay. All right, so today is Euler's method. All right. All right, so we're going to read it, and then we're going to do a couple problems, and that'll be that. Okay. So, yeah, so I guess it's good to recall what we did last time, which was slope fields, which was you have some differential equation, you take a whole bunch of points, and you evaluate the slope at that point, and you make a slope field plot. And we showed that for whatever, let's just get into it. So, the geometric concept of a slope field, as discussed in the previous section, is closely related to a fundamental numerical method for approximating solutions to a differential equation. That's a good point. Yeah. Okay. Given an initial value problem, we can get a rough idea of the graph of its solution by first sketching the slope field in the ty plane, and then starting at an initial value t0, y0, sketching the solution by drawing a graph that is tangent to the slope field at each point along the graph. In this section, we describe a numerical procedure that automates this idea. Using a computer or a calculator, we obtain numbers and graphs that approximate solutions to IVPs. Numerical methods provide quantitative information about solutions even if we cannot find... Give it a sec. Even if we cannot find their formulas. There is also the advantage that most of the work can be done by machine. The disadvantage is that we obtain only approximations and not precise solutions. If we remain aware of this fact and are prudent, numerical methods become powerful tools for the study of differential equations. It is not uncommon to turn to numerical methods even when it is possible to find formulas. Most of the graphs of solutions of differential equations in the text were drawn using numerical approximations even when formulas are available. I don't understand that. If you know that there's an analytic solution, why would you bother? The numerical technique that we discuss in this section is called Euler's method. To describe Euler's method, we begin with the IVP. Since we are given f of ty, we can plot its slope field in the ty plane. The idea of this method is to start at t0, y0, and take tiny steps dictated by the tangents. We choose a small step size, delta t. The slope of the approximate solution is updated every delta t units of t. In other words, for each step, we move delta t units along the t-axis. The size of delta t determines the accuracy of the approximate solutions, as well as the number of computations that are necessary to obtain the approximation. So starting at t0, y0, our first step is to the point t1, y1. T1 is going to be equal to t0 plus delta t, and t1, y1 is the point on the line through t0, y0 with the slope given by the slope field at t0, y0, i.e. f of ty, or f of t0, y0. At t1, y1, we repeat the procedure, taking a step whose size along the t-axis is delta t and whose direction is determined by the slope field at t1, y1. All right, so we've described this iterative procedure. Continuing, we keep doing the thing. Okay, here's a good picture. This shows what's going on. So this is the actual solution. All right. All right. Okay, so we already described how to find the next time point. by just simply adding some predetermined delta t. But okay, to obtain the y, we know that the slope of the solution to the equation dy dt at the point tk, yk. So basically we need to draw a line through tk, yk up to tk plus 1 f of tk plus 1. Wait, let's see. So this is going to be wait, I'm a little confused by this term. F of tky delta t. Why does that give you the rise? Let's say we have like f of ty is equal to 2t. So we just have this. So let's say tk is equal to 0, delta t equals 1. Then what we have is okay, yeah, sure. That tells you how far to go. Now we can use our basic knowledge of slopes to determine yk plus 1. The formula for the slope of a line is the difference between yk plus 1 minus yk divided by delta t. So that's delta t. So we have yk plus 1 minus yk over delta t is equal to f of tk yk. Right, so that's how they arrive at that. Okay. Okay, great. So now we have derived Euler's method. Here's the description of it. Given the initial condition y of t0 is equal to y0 and the step size delta t, compute the point tk plus 1, yk plus 1 from the preceding point by using the differential equation to compute the slope. Calculating the next point by calculating the next time point by adding delta the step size, and then computing the next y point by adding the previous y point plus the slope of the tangent line through tk, yk, and then multiplying that by delta t. Okay, approximating an autonomous equation. To illustrate Euler's method, we use it to approximate the solution to a differential equation whose solution we already know. In this way, we are able to compare the approximation to the known. Consequently, we are able to gain some insight into the effectiveness of the method and seeing how it is, in addition to seeing how it's implemented. Wow. Okay. Okay, they solve it. Approximate the solution over the interval 0. Okay. In order to approximate the solution over an interval whose length is 1 with subset 0.1, it's going to be 10 iterations. Okay, we get the initial condition here. Given delta t is equal to 0.1, we have t1 equals 0.1. Compute the y coordinate by the procedure. Okay, here we go. There's the simulation. Let's see. This is not a good approach. We'll see how to avoid this. The reason for the error can be seen looking at the graph of the solution and its approximation. Now, what's the error? Do they show the error? .8 versus 3.8 versus 4.2. Still pretty bad. That's pretty good. 0.01. So you have to take what, 1,000 steps? No, 100 steps. Okay. Okay, so the last example was autonomous, meaning that it doesn't depend on t. However, if the differential equation is non-autonomous, the value of tk also plays a role. To illustrate that, let's do it on a non-autonomous case. It turns out it's separable. Yeah, we can see that. F equals to minus 2t and g equals y squared. Okay, so they separated and integrated, and they got that. We use Euler's method to approximate the solution of the interval 0 to 2. Okay. In Chapter 7, we present more complicated algorithms for numerical approximation of solutions. Although the algorithms are more complicated from a conceptual point of view, they obtain better accuracy with less computation. All right. RC. Okay. Recall from 1.3 that the voltage VC across the capacitor in the simple circuit is shown by this differential equation. we have seen how we can use slope fields to get a qualitative sketch of solutions. Using Euler's method, we can obtain a numerical approximation. Okay, so we consider when the voltage source is a periodic. Okay, so yeah, sine of t. The voltage oscillates between -1 and each unit of time. The differential equation is now wait, RC, okay, it's over 2. Oh, over 0.5. Okay. Yeah. So that's pretty obvious. From the slope field of this equation, we might predict that the solutions oscillate. Using Euler's method applied to this equation for several different initial conditions, we can see that the solutions do indeed oscillate. In addition, we see that they also approach each other and collect around a single solution. It's pretty cool. Okay, so let's look at errors. So we have this differential equation, and we'll see that numerical solutions are can be problematic. There are equilibrium solutions for this equation if sine y is equal to 0. In other words, any constant function of the form. This is actually an interesting differential equation. I don't know what the integral of 1 over sine y is, but in other words, any constant function of the form y of t is equal to n pi. Okay. This problem is typical of the use of numerics in the study of differential equations. Numerical methods, when they work beautifully, but they sometimes fail, and we must be aware. Okay. Yeah, it's pretty nuts. We have now introduced, okay, so this is a pretty quick read, actually. We've now introduced examples of all three of the fundamental methods for attacking differential equations: analytic, numeric, and qualitative. Which method is best depends. Okay, great. So, all right, so just simulate. I don't know if we need to do that. Okay, make a table. Um, Wait, what is the difference between 1 through 4? Oh, I think that, okay, so this is simulate with a computer and this is do it by hand, I think. I'd like to do 11. 11 looks pretty fun. Yeah, my guess is that something goes wrong when you cross this 0 because the step is going to compute a value. Well, actually, if delta t is 0.5, then we probably will get. Oh, no. Hold on. So, okay, so the initial value is going to be 3 times 1, which is 3. So it's going to be up. When w gets to 3, which I'm guessing it does, it's going to jump over the 0 and keep going up or something like that, which is actually incorrect. So that's probably the answer to 11. Okay. I use Euler's method to determine how long it will take the diver to reach 95% of terminal velocity. Uh, what I'm guessing is that because this is an autonomous, both of these are the same autonomous differential equation, that you're going to get the exact same graph. So they should be the same. Compare your answers to 5 and 6. Now 5 and 6 is Euler's method doing a good job in this case? What would you do to avoid the difficulties that arise in this case? That's actually an interesting question. Is there a threshold for step size at which point it like never has the problem? Or okay, which problems do I have to do? Number 3. Okay. Wait, there's no less than or equal to? What? What, bro? Oh, it's just LT. It's probably LTE. Is it this one? Why is it bold? Why is it so much bolder than the other one? Okay, that's it. Did this render properly? No, wait. I think this needs to be capital delta. There we go. What's going on, Ab? Okay, so there we go. So that's the specification of the differential equation. I wonder how they want us to do this. Actually, what is the recommended? I mean, I'd probably just write it myself so that I can do it like an embed thing of code because I kind of want to use that minted thing, you know? I want to put pretty looking code in my. Whoa, how insane is that? Okay, let's just do this. F signature is, yeah, TY. And it's going to take a scalar. So we're just going to, do I need to have it return a, let's see. It's kind of funny that there's really no, I mean, SciPy, dude. SciPy is a freaking donkey. Everyone knows SciPy is a donkey. Okay, let's just see if I can write it myself. I want to embed Python code in this. So this is going to be, fun 3 is ready. T is equal to, did I write it down? Y squared minus, is it 4y or 4t? 4t. Okay. So now we're going to call Euler of f. Let's see, what is the initial condition? Okay. So this is going to be f t0. Oh, wait, I got this wrong. Delta t is 0.25. Okay, so 0.5, 0 to 2. Okay, good. So we have t0, which is 0, y0, which is 0.5. TF is 2, and dt is 0.25. Okay. T is y's equals this. And I think we need to import. I want to try that. UV add. Wait, let me look it up. I want to use some new stuff, you know. I want to just have some fun with this because something new. I haven't done it in a long time, so let's just do polars Python. Polars has got to be better than data frames from the new era, bro. All right, let's just do it. How do I get started, bro? Why is it so pip install polars? Oh, cool. All right, so let's just print t as well as uv run hello. What? Oh, I think it's because I have to do this. Maybe this? Oh, wait, I'm so slow. There we go. Okay, so now I wonder if they have something for. Is there like a types Python? Like, is there like a thing? Um, because what is it that I want? I want something that like takes my data types in. Oh, see, no, that's stupid. That's not what I want at all. I want the other one. Oh, sys inputs. Oh, that's cool. Yeah, so I mean, it's because I use the online one that I don't think I really need all that, but so this is gonna be T's, and then Y is hold on, I want this to be interactive, so it's. Wait, can I do Shift Enter? Ugh. What? Makes no sense. Dude, Python is still such a shit experience. It's kind of insane, actually. Okay, so how do I unwrap? Just the map lambda x0, yeah, like that. Does that work? Why is this? I guess I need to do list too, right? Python's such a joke, dude. Wait, why is this not even working? Oh, what? What the fuck are you talking about, brother? Jeez. Wait, why is this? Oh, because this needs to be a dict? Is that what's happening right now? So that's that. Oh, there we go. That's such a weird freaking thing, man. Let's see if this looks at all like what I want. Oh, nice. Perfect. Okay, so now what I want to do is uh I want to like, oh wait, I can do this now? Oh, nice. Oh, sweet. That worked so well. It's not as good as Julia, but it's like what I've been hoping for. Okay, great. That's sweet. Okay, so I can actually use Python now. I've been wanting to use Python for so long, but Python is just so garbage. But at least they have this thing where I can just type my code, and because I hate IPy notebooks. I really don't like them. So now what I want to do is there a thing? Um, so let's see. Type CSV. Okay, great. Okay, awesome. Okay, great. That's what I want. So what we're gonna do is now df.toCSV or something. How do I export? Write CSV. So this is going to be problem 3 table. And let's just make sure that 1, 2, 3, 4, 5, 6, 7, 8. Wait. But we need one more point. We need 9 points, 8 steps. A range. So A range, how do I include the endpoint? Because like if I do, so T's, right, np.a range. Is there a thing where I can do this? And actually, you know what I want? Let's see. Okay. If I do IPython and then I shift enter this again, because IPython, because the problem is the default REPL in Python is so bad. Yeah, so this just opens up a, okay, but at least it works. What just happened? Okay, so right. So np a range. Where's my uh, that's goofy. Oh, that's so funny. Okay, whatever. Yeah, so let's just do this. So if I do point 2.1, and I put TS. Okay, great. So that's what I need. Okay. Okay, and now I should be able to go to my document here. So okay, wait. Embed Python code text. No. I want I don't want to run Python code. Although that's kind of cool. I want Python. I'm not scripting. Math, symbol, layout. I should read the foundations page, but I'm definitely not doing that. In types, how do I put nicely formatted code? I don't want it. Let's read this foundations. Never mind. I'm not reading. I know. Isn't it minted? See, that's pretty cool. Because it has to have, what's it called in it? Like tree sitter or something. It has to have a grammar thing with it. Where's my other? Is that really all you have to do? Oh, that's actually really nice. I feel like it might be making that up. Oh, beautiful, man. That's really cool. Okay. So we have this, and what do I need to say? The a detail is np dot a. Oh, do I have to do? How do I do that though? Oh, I have to go. No, see, how do I do it inline? Inline code. But is there a way? I feel like I might need triples. Um, well, anyway. Oh, really? That's what I have to do? That's pretty cool, but it's also really annoying. Because then for all of these, I gotta do TF equals 2.1. A little less convenient. Oh, but you can't put it in backflips. Yeah, there we go. So this is np dot. All right, so let's just copy the code over. Okay, the table of results. I need to actually go there. And I need to do this file, upload file. Oh, is that gonna work? Why didn't that work? What in the hell, bro? Reveal files. There we go. Actually, is that CSV right? Yeah. I mean, I don't actually know if that's right or not. Oh, but this code is not ready yet because I need to plot it too. Okay, so now let's do that thing with the table. Blah, blah, blah. Table, table, table. Where is it? Where did I find that? Okay. This is going to be... Should I include the y dt? Yeah, maybe. Is there a way to just tell table? I mean, that is pretty cool. Oh, that's funny. And what if I just... Okay. That's good enough, right? That's good enough. Okay, so now we just need to do the... Is this going to work? There we go. That's sick. I mean, we should sanity check this with a couple of like real calculations. So for instance, our initial condition, t is 0, y squared is going to be positive. Yeah. Or I mean, yeah, y squared is going to be positive. So it does go up slightly, and then it goes down. So you know what I'm going to do, actually? I'm going to do... wait, why does it need to be t's dot size? Oh. Right. Yeah, let's do this. No way. All right, so let's rerun it. What? Oh, you know what? I think it's frozen. There we go. dy dt is not 1 there. That doesn't make any sense, right? I don't think that's true. So it's going to be t's at 0. Man, this stuff always takes longer than you think it's going to take. It's not even that hard, but it just takes forever. F of... So... Yeah, so I think this is wrong. Where's the table? All right, so let me just ask because t's is definitely 0. And F, let's just call f of 0. Yeah, that's what I would expect. Did I? Cause should. Oh, you know what it needs to be though. It needs to be this. And I think that we actually want this to be. I think that's closer to what's right. And the last step, let's just make sure the last step is right. What is setting it to 1? Okay, let's do this too. Right. And we can rewrite this to be t0. What? I just defined tf. Oh, empty is really weird. Empty is sus as hell, dude. Whoa. Wait. Okay, wait. I definitely did something wrong. Oh. Yeah. Okay, this looks right except for the very last one, which is missing. Can we just do is there an end? How do you do the end? There's no way to do this, right? How do you do that? And do you have to do len? I'm so not used to this. Um, but actually, you know what we could do? We could actually just do this. Oh, we can just do -1. Okay. All right, that's good. Let's see, does this work? Okay. We can get rid of this now. And then we can ask, is there anything wrong with this code? Do you see anything wrong with this code? All right, so yeah, so we got our. I'm pretty sure that this is right. That our last point. Okay, so it showed that. That's fine. Oh, that's nice. Is this gonna work? I don't think this is gonna work. Can we look at this? Oh, nice. Okay. What do I format? What? There's no formatter? Maybe it's just that I don't have the extension on. Why would I ever turn that off? Whatever. I don't really care. I actually do care though. I just don't really want to deal with it right now. Wait, what if I just do this? Format document. That's lunacy. That's actually insane. That's really what the default Python behavior is. It's the most popular programming language in the world, and that's actually how it does it. Jeez Louise, bro. totally insane. Wait, is there not? There's probably like a UV format or something. Does UV have a formatter in it? I bet the people who makes UV again. Astral. Astral has a rough. That's what I want. I want rough. How do I get rough? I should be able to just do like UV add rough. I don't know. Tutorial. There we go. See, oh, I love Astral, dude. These guys know what's up. How do I run the formatter? Sick. All right, we're starting to get somewhere. It's a little slow in the get, but you know. Okay. This is what I wanted. Because I knew that this freaking lambda was stupid. Nice. All right, so let's just run the thing again. So why is it giving me an ad for black? Who wrote this? It's written in Python. I don't think so. Look at how ugly this logo is. I'm all about rough. Rough. Ooh, a freaking dog, bro. I'm a dog for Python formatting. All right, where's my marker O? Okay, so now we just need to upload it. Oh, we need to re-upload the. Oh, I dragged and dropped it. Oh my god, is that really what happened? Okay. Okay, and let's do this. And then we just need a page break. All right. Looking pretty good, man. I think we did the entirety of the problem, right? Is there anything else that we need to do? Euler's method. Euler's method. Okay. So problem 9. Wait, I want to actually check if that table is right. Can I look at the table? I'm pretty sure that's right. I gotta say, man, type's actually pretty good. I kind of like it. It's more productive than LaTeX, and it's more flexible too. Like LaTeX, bro, LaTeX just it's so donkey, man. I wouldn't call types the goat because I just don't think typesetting is that cool. But you know, actually, let's include the full code. All right, let's do page break again. What is problem 9? Wait, I'm actually so confused though. Are we allowed to use a computer? I mean, there's just no way that they make us make 100 steps by hand. That would be crazy. That'd be totally insane. Alright. There's just no freaking way that they're gonna make me um oh really? Oh wait, you know what you need to do? You need to do this. Okay, cool. Yeah, I mean, there's no way they're gonna make us do 100 steps. That'd be totally insane. 2 p.m. Okay. How long have we been doing this? An hour? Not that bad for 2 problems. Okay. Um, Okay. Where were we? We now need to, okay, so let's, okay. Okay, so the first step is y1 is going to be equal to y0 plus delta t f of y0 or t0 y0. This is the formula. So this is going to be equal to, so let's do this thing. This one's go that. Okay. Wait, what? How did I do this last time? Is it this? This is what's so stupid about their evaluation mechanism. What? You can do times, but you can't do x. I mean, what is that about? That's so ridiculous. Or is it calc? Dude, calc mechanism is so ridiculous. Hold on. I have a Discord. It's such a joke. I don't. Yeah, okay. Type's a bunch of malarkey, bro. A bunch of malarkey, bro. A bunch of freaking malarkey. Okay, so I think what I have to do is do this, and then you do calc.path. What a joke, dude. Why do I have two equals? Law. Oh, you know why? Oh. Is that actually true? 0.2 squared is equal to. Is that true? La, la, la. So it is positive, right? Oh, I think I should just be able to do this. Okay. I am talking to you, and you're talking to me. I need to do this bullshit. It's so fucking lame. I have to go calc. But let's just finish this thing up because I'm actually getting sick of this thing. All right, let's now we can just go down here. Okay, what are the parameters of this thing? Can we write this down? It's so 9 is y dot equals y squared minus y cubed. Y 0 equals 0.2. T in 0 to 10. Delta t equals 0.1. Okay. So let's just do that. So y0 is equal to, did I have to do that? Yeah. All right, let's see if this works. It actually is increasing. But wait, that doesn't make sense, right? Okay. Yeah. Okay. So wait, hold on. Let's actually think about this. So if you factor it, it's y squared times 1 minus y. I mean, unless y is actually negative, this thing is not going to be decreasing. So it's if y is greater than 1, however, then it'll decrease. But it's going to increase to 1. Let's plot it. Let's integrate it. It says I'm getting chat messages, but I don't see them. Okay, what am I looking for? What am I trying to do? Oh yeah, integrate. Oh no, I'm trying to check if. Oh yeah, I'm losing all the chats. Damn. I missed all of these chats, guys. That stinks. Yeah, I'll do some more lean at some point for sure. What am I doing? How am I? I'm good. We're doing differential equations stuff right now. I'm just doing homework, simple as that. Just doing some homework. Um, but I do need to integrate. Who's DMC? I forget. Yeah, I do got to do more lean. I've been gotta pour up. Oh, I don't know how to do partial fraction. Is there a simpler way? Yeah, man, I don't remember how to do that. And we only get a general implicit solution. So actually, hmm, okay. Explicit. What is Lambert W? That's cool. That's neat. All right. I gotta watch out for these chats. Let me just keep my phone open, maybe. How am I doing it with Python? I mean, it's called numerical integration, and it's basically just you discretize the slope field into a bunch of small segments of lines, and as you trace that path, you'll get something that approximates the solution of any differential equation. So that's that. Okay, what are we doing here? We are going to export this CSV, and we're also let's just copy this over into yes, numerical integration is the coolest thing ever, man. Nobody actually solves these things for real. Um, Thank you, bro. Thank you. Subscribe, man. I do a bunch of cool stuff. I built a ton of stuff. Um, Thanks for the sub, bro. That's really nice. It means a lot. All right, so what we are trying to do now is we're trying to make this plotting function inspect. I've never seen that before. Oh, that's so sick, actually. Wait, I actually really want to look at this. That's so cool. I didn't know about that. All right, so let's put this function here. Oh, I didn't know about this dollars. I think this oh, you know what? I think that's actually LaTeX. Wait. You need to give it the T's and the Y's. Oh, that's fine. Yeah. All right, so let's evaluate this. Let's do this. Plot Euler solution. Inspect is not defined. Oh, yeah. We're going to need to import inspect, import read. All right. All right, so let's see what's going on here. Let's try to run it again. Is it going to do what I think? No, see, that's so silly. No. Yeah. Not REPL defined. Oh, geez. Okay, well, whatever. It doesn't matter. We'll just give it the body. That's fine. OD Easter. We'll just say. Oh, I gotta close the other one. All right, that one works for me. I'm fine with that. Oops. Wait, what did I just do? Okay. So we can save this. This is going to be problem. I never knew PNG stood for that. It's kind of crazy, actually. All right, so let me just make sure that the table has 100 and so we took 100 steps. Yeah, I think that's right. There's 102 lines. Okay. All right, so let's just finish. I wish I had Copilot built in here. Because it's like, all right, this is getting pretty boring. All right, cool. Getting there. Okay, so first we get 0.2, 0.1, 0.203, 0.2, 0.206, 0.3, 2. 3 decimal round of deflection. Okay, so now I got to upload the CSV and the plot. So first we are going to upload first data, use data from 9 table. And then we need to go to downloads from 9 plot. All right. Now we need to do this. Wait, did it not upload? Oh, why didn't it upload? I don't know why I didn't upload. Wait, what? What the hell is going on here? Wait, upload is just not working. Why is that? Is it because there's an error here? That would make no sense at all. What if I lost my whole homework just from doing that? That'd be so annoying. Oh, it's working now. There we go. And it said provide a table. Am I really misinterpreting it? I feel like I got it right. Okay. All right, so I think I'm done. with the homework. All right, so one thing I want to do is I just want to say no. Uh, okay. It's so weird that A range you need to do this stupid hack. I don't really care about that. You wrote DV. Okay. So now let's just open up. I hate that you can't like go to dashboard. Oh, I hate that. It's just so stupid. Like, why don't you just let me make a bunch of tabs? I want a bunch of tabs. So I'm gonna turn in this homework soon. Oh, that's what semi-stable means? Oh yeah, semi-stable. We haven't gotten to that, so I feel like it's okay. Last one. Wait, number 30. What? Oh, wait. Um, oh, it is 37. Wait, did I do this wrong? 37. This is 1.2. Oh, fuck. Oh, damn it. Okay, shit. All right, so we got more stuff to do. Damn. Could have sworn it's a. Hey. Three t squared y squared. 2ty squared. Okay. Damn, I can't believe I did this. I need to double check that I actually did all the right problems. Okay. All right. Let's just do this on paper, and then we're going to do it. Okay, so the idea here with this one, just make sure it looks right. 2ty squared, so dy dt is equal to 2ty squared plus 3t squared y squared. And then the initial condition is a y of 1. See, this is the problem, man. You gotta be careful. It's really easy to make a little mistake on this stuff. Okay. So yeah, so the idea here is you factor out the y squared, and then it becomes a separable differential equation, and you can integrate both sides. So what that's going to give us, so let's just do it on here. So we can factor y squared. Diff y over y squared is equal to 2t plus 3t squared. Jesus, I hate that. So annoying. Diff t. All right. Okay. By linear t of integral, we integrate the right hand side integral because of linear t of integration. So we're going to get, so integrating 1 over y squared. So let's just do int integral diff y squared t plus 3 integral 3t squared diff t. Okay, now we get, so power rule on left-hand side, power rule applies to all 3 sub-expressions, giving the integrals. So we're going to get, so this is y to the minus 2, so we're going to get y to the minus 1. We're going to get minus 1 over y. I'm almost positive it's that. So we're going to get minus 1 over y is equal to, and then we have 2t, so we're going to get t squared plus t cubed. So we're going to get that. So what we're actually going to get is y is equal to minus 1 over t squared plus, or let's do, and plus c there. I'm so bad at keeping track of the c's. Someone chat. Hold on. Let's see. It's loading. Is this separation of? Yeah, we're doing separation of variables. So, so disregard. Here, let's do this. So this is what we're working on right now. Is 37. So you factor the y squared, and you get dy over y squared is equal to 2t plus 3t squared dt. Let's zoom in a little bit so people can see it. Okay, and so this gives us these integrals. And because All right, so we should be able to get basically minus 1 over y plus c1 is equal to, we're just going to add all of the c's, and then we're going to get rid of the c's as they come and go. So then we're going to get t squared plus c2 plus t cubed plus c3. Okay. Combining constants gives solve for y, find solve for y by multiplying by y and dividing by. So now we're going to get y is equal to minus 1 divided by t squared plus t cubed plus c. And I don't know. I don't know exactly how. On the AP test, where's the spider? What? Wait, where's the what? What are you? Other wait, no, what? What are you guys talking about? Is there really? I can't see anything. Hold on. I honestly don't see it. On the branch? Well, anyways, it's probably a harmless spider. On the AP test, I have no idea. I don't actually know what they expect. To be fully honest. Um, okay, wait. Yeah. So I'm actually just gonna ask ChatGPT on like how do I handle the C because I don't really know. Like I don't know if I can take it out of the denominator. You leave it in the denominator. Okay. All right. So we get wait, where am I? I'm looking for this is the general solution for the R. Okay. All right. We can now find p using the initial condition. So for the initial condition, we had y1. So this is going to be y of 1 is equal to minus 1 over 1 squared. Oh, no. Minus 1. Wait. Let's do this. Wait. Am I doing this wrong? Yeah, so C. All right, so C is equal to minus 1. The particular solution to this IDP is, and we can just copy this. All right. All right, cool. So we can I'm gonna end the stream and turn all this stuff in on Canvas. All right, so I'm gonna download this actually. And then I'm gonna delete this problematic one. I'm also gonna make sure that I'm also going to homework 3. This is homework 4. This is homework 3. 13 and 19. Okay, great. So, and then let's just make sure that it's homework 4, 3, and 9. All right, dodged a bullet, man. All right. Okay, cool. I'm glad you all joined me. I know we had a little bit of a mix-up. I mean, a lot of this wasn't Euler's method, but for the most part, this is an Euler's method focused stream. Went over the sections and all of that. All right. Peace out.